All right, this is chapter 14, part 2. We are on slide number 9 in the PowerPoint. And so we've introduced the idea of rate. We talked about the rate of different components of the reaction. Now we need to actually get into how we measure the rate if we're given a set of data and we have to make a graph. Okay, so I have a graph here of the concentration of a reactant molecule in a reaction versus time. Now, how do I know it's a reactant? Well, reactants, I usually start with a large amount of reactant, and then over time, the concentration is going to decrease. If it were a product, the concentration would be increasing over time. So obviously, by looking at this graph, I should be able to tell it's a reactant that's being measured. So when I look at it, we mentioned before, the speed of the graph can correspond to how steep the decline is on the reactant. So if I want to actually calculate the speed itself, the steepness, that means I'm going to be measuring slopes. Okay, so we can measure two types of rate. First of all, the instantaneous rate is basically how fast the reaction is moving at any given moment. Okay, so on this graph, if I can find the slope at any given point, then that's going to give me the instantaneous rate. All right, how do I do that? Well, I'm going to draw a tangent line. So anywhere on the graph, I should be able to draw a tangent line to the curve. If you remember, a tangent line should only touch the curve at one point. So if I said draw a tangent line at 3 minutes, or how fast is the reaction going when 3 minutes have passed? I would go to 3 minutes, I'd go to the curve, find that point, and then I would try to draw a tangent line where the line only touches the graph at that one point. Once I have that line, then I have to determine the slope of that point. Okay? So that's instantaneous rate. You find the point that you're interested in, you draw a tangent line, and you find the slope. The other type of rate that we're going to talk about is the average rate. The average rate is going to be over a period of time where you're going to be given an initial time and a final time. It could be the whole experiment, or it could be the first 5 minutes, or it could be the average rate between 5 and 7 minutes, right? They're always going to give you a range that you have to look at, okay? Well, that one also is going to be pretty straightforward, where if we do over the entire experiment, I just consider my initial point here, my final point here, and I'm going to find the slope of the line between those 2 points. Again, how do you find slope? You determine you pick 2 data points on a line, do the change in y on top, divided by the change in x on the bottom. That's your slope. Okay? So the equation slope equals y2 minus y1 over x2 minus x1. So here's an example. Given the graph, and you should kind of look at these numbers on your own and just make sure that you're capable of doing these calculations. But if the question said calculate the instantaneous rate of the reaction at t equals 2 seconds. So I go to 2 seconds. On my x-axis, I go up to the graph. I draw a tangent line the best I can. And then I have to pick 2 points on that line. So they picked the first point right here is 3.95 seconds and 0.3 molar. And then they found another point, 1.15 seconds and 0.6 molar. So then they did the final y value minus the initial y value, so 0.3 minus 0.6. And then they did the final x value, 3.95 minus 1.15, right here. And then that's going to give me a negative answer, which we said the rate has to end up being positive. So that's why they put a negative in front. So we're finding the slope of a reactant, which is a negative number, but then at the end we're making it positive. Now, moving back a step in this process, if we do this in lab, which one of our experiments that we do in lab every semester, you go into the lab, we do a reaction that involves a red dye usually. We can calculate by measuring the absorbance of light through the sample, we can calculate how much red dye is in the solution. So, just given that information, I have a reactant, I measure its concentration over time. So I measure the concentration at the beginning of the experiment, then at 15 seconds, and 30 seconds, and 45 seconds, and so on. So I have all these data points between concentration and time. I'm going to turn that data into a graph. Plotting the concentration versus time. It gives me a curve. And then again, just like we said before, I could ask you on a test, if I gave you this graph, to calculate the initial rate of the reaction. What's the initial rate? That means the rate at the beginning. That's a specific point. So this is the instantaneous rate at time equals 0. So the first point, again, I would try to draw a tangent line, and then I would find the slope. Now the question, would everybody in class draw the tangent line the exact same way? The answer is no. Okay? We don't expect everybody to get the same answer, but you should get close to the same answer. Okay? If you draw a reasonable tangent line, there's a certain range of slopes that we would probably accept. And your goal is just to be within that range. But again, we're reasonable about it. We just want to see that you know how to go through the process. Okay? So for the initial rate, it'd be the slope of the tangent line from the first point. And then the second question, calculate the average rate between t equals 0 and t equals 15 seconds. So that's where I would take these 2 points and do the change in y between those 2 points divided by the change in x between those 2 points. Okay? I'm going to leave that for you to work on. Ask questions if you need to. So now, we know how to calculate the rate. We know how it looks on a graph. But now we need to talk about, with a given reaction, how does the concentration of the molecules affect the rate? Like, if I set up an experiment, if I mix more reactants into the solution, I expect more collisions, and therefore the rate's going to go faster. Okay? If the concentration of a reactant is lower, then there will be less collisions, and the reaction will go slower. So these are things that I have some control over, but I want an equation I can plug into to actually be able to calculate or predict the rate. Okay? So this equation here is called the rate law. Basically, it relates the rate of a reaction to the concentration of each of your reactants. And again, this equation I have set up for 2 reactants, but if there was a third reactant, it would just say times concentration of reactant 3. Each reactant is raised to an exponent. Those exponents are called orders. Okay? So the first order is m, the second order is n, the third order could be O or P or whatever, it's just some letter reason as a variable, but each reactant can be raised up to a power that needs to be determined. There's also, in the front of the equation, K is a proportionality constant. It's called the rate constant. Okay, so my rate law is going to set up like that, and basically we can do experiments to determine what the exponents are supposed to be, and we can determine what the value of K is, so that then if I plug in any given concentrations for my reactants, I should be able to predict what the rate of the reaction is going to be. Okay, so we want to make this a usable equation. Again, that's a lot of information, but once we look at a couple problems, it'll simplify. So we use this equation to predict the rate of a reaction when the concentrations are known. K is the rate constant. Now, key with the rate constant, K is going to be different for every reaction. Okay, and it does change with temperature. So K, the rate constant, it's a value that gives you an idea of how fast a reaction is going to go. Well, if I heat a sample up, most of the time reactions go faster. And the only part of the equation that can change with temperature is actually K. If I raise the temperature, K changes, and then that can affect the rate. The exponents are called the orders. Each exponent, like I could say the order of reactant 1 is M, the order of reactant 2 is N, and then if I talk about the overall order of reaction, that would be the sum of the exponents. So the overall order of this reaction, if it's only 2 reactants, would be M plus N. So let's just say if reactant 1 is first order, reactant 2 is second order, so that's a 1 and a 2. The overall order would be 1 plus 2. the reaction will be third order. All right, so we need to do some experiments to get this rate law into usable form. We need to be able to solve for all the constant values that we need. So we're going to use a method to do this called the method of initial rates. The initial rate, we already said before, that's going to be an instantaneous rate that we can determine from the graph at time equals 0. So the first data point, draw the tangent line, find the slope, that's what the initial rate of reaction is. Now, again, to do this, we're going to make some assumptions. Okay? Number one, we're going to assume that when we set up an experiment, if we know exactly how much of each reactant we're putting in there, then we know the initial concentrations of all the reactants. That's needed. We're going to assume that before the reaction happens, there aren't any products present. We're assuming there's no reverse reactions going on, no side reactions where there's other stuff forming in there. We're focused on there's one reaction going on. It's the reaction we want. And then we know how to calculate our rates. All right, so we have a reaction. Don't worry about the structures here very much, but the first molecule is called methyl acetate. It's reacting with sodium hydroxide. Now the sodium is actually a spectator, so it's actually going to refer to hydroxide through most of the problem. But methyl acetate reacts with sodium hydroxide to form acetate and methanol. We're really not even going to worry about the products at all. All our calculations are going to be based off of the reactants. So now let's go to the next slide. So the method of initial rates. What we're going to do is we're going to perform the same experiment several times. But each time we do the experiment, we're going to slightly change one of the concentrations of the reactants. Okay, so I look at this data table. The first row is experiment 1, where I mix together 0.05 molar methyl acetate and 0.05 molar hydroxide. So those two things were mixed. I collected the data. I built the graph. I determined the initial rate at the beginning from the first point, and the value that we got was 0.00034 molar per second. Okay, so that's one experiment. That's all the data. In experiment 2, I did the exact same thing, except I changed one thing. I changed the hydroxide concentration from 0.05 to 0.1. And I basically want to see, okay, I doubled the concentration of hydroxide. What's going to happen to the rate? That's what I'm trying to figure out. Okay? And then we'll come back in a minute. Experiment 3, again, this time I changed the methyl acetate concentration. I doubled it to see what effect that would have on the rate. By doing these little variations, I'm going to be able to solve for the rate law, plug in all my constants, and figure it out. So now we're going to do that. I'm going to shut off the PowerPoint and work on the chalkboard from here on. So if you haven't written down the values, go ahead and write those down. But essentially the method of initial rates, we're going to take the rate law, which I'll write out the rate equals K times concentration. The first reactant was methyl acetate, so I'm going to call that MA. It's raised to an exponent. I don't know what the exponent is. I actually prefer to use X and Y as my exponents. So I'm going to methyl acetate to the X times the sodium hydroxide or hydroxide to the Y. Okay, that's what my rate law needs to look like for this experiment. Two reactants raised to exponents with the K in front. If I can plug all these in, it'll give me the rate of the reaction. Okay, now, I'm going to plug in for the first two experiments, I'm going to plug in all the numbers. Specifically, I'm going to do experiment 2 over experiment 1. Okay, and when I do that, it's going to allow me to solve for some of the values that I need to figure out. So, experiment 2, the rate, which is in the far right of the table, the rate for experiment 2 is 0.00069 molar per second equals K. We don't know what K is yet, so I'm just going to write K. Times the concentration of methyl acetate. In experiment 2, concentration of methyl acetate was 0.05 molar. Raised to the x power, I don't know what x is yet. Times concentration of hydroxide. In experiment 2, hydroxide is 0.10 molar. Raised to the y. All right, so that's my rate law for experiment 2 with everything plugged in. I'm going to divide that by experiment 1, all the values. So again, the first value, the rate for experiment 1 was 0.00034 molar per second. I don't know what K is. The methyl acetate is 0.05 molar raised to the x. The hydroxide is 0.05 molar raised to the y. So those are all the numbers in the bottom for experiment 1. Now I can look at this and divide these. And if I divide 0.00069 by 0.00034, I'm going to get, I'm pretty sure that comes out to be about 1.03. The units cancel. Equals, excuse me, 2.03, sorry. 2.03. Divide K by K, anything, same thing, top and bottom, this cancels out. 0.05 to the x, divided by 0.05 to the x, again, that cancels. And then 0.1 to the y, divided by 0.05 to the y, if you remember basic algebra rules, like let's just say I had 6 to the y over 3 to the y, when two numbers have the same exponent and you divide them, you can divide the number in front and then just keep the exponent. So that would equal 2 to the y. Okay? That's separate, but that is a mathematical rule for dividing numbers that have exponents. So I can divide 0.1 to the y, divide by 0.05 to the y. 0.1 divided by 0.05 is 2 raised to the y. At that point, I've simplified, I got rid of a lot of stuff, so 2 to the y equals 2.03. Now, realistically, like the order is supposed to be a whole number. So if y is a 1, 2 to the first equals 2. That basically is what we're saying here. Remember, experimental data is not going to be perfect. But let's just say if y was a 2, 2 to the second would equal 4. That's not right. 2 to the 0 would equal 1. So the only number here that makes sense, y equals 1. So by dividing experiment 2 by experiment 1, canceling things out and simplifying when I can, I have determined that the value of y in my rate law is a 1. Now, let's just say the numbers aren't this clean. How do you actually mathematically solve for that y value? What you would actually do, take the log of both sides. So I'm going to do the log of 2.03 equals the log of 2. When you take the log, the exponent can come down in the front and be multiplied. So it's going to be y times the log of 2. And then I can divide that over. So y would equal the log of 2.03 divided by the log of 2. And again, that should come out to be pretty close to 1. We always round our orders to a whole number. All right? So that's it for that one. Now we need to do another comparison to find x. Now what you might have noticed, when we compared experiment 2 to experiment 1, The only difference in those two experiments was that we changed the value of hydroxide. If we change the value of hydroxide and then compare the numbers, that allowed us to find the exponent of hydroxide. So now when I look at the experiments, I need to find two experiments where everything's the same except I change the concentration of methyl acetate. If I can isolate methyl acetate as being the only change that occurs between two experiments, that's going to allow me to solve for X. Okay? So when I look at the table, specifically, if I look at experiment 3 and experiment 2, the other concentration stays the same. That would be the hydroxide, because I've already studied that one. So I want it to be constant. I only want to change one variable at a time. And this time, I want it to be methyl acetate. So, experiment 3 divided by experiment 2. Again, we just plug all our numbers in. So it's going to be 0.00137 molar per second equals K times methyl acetate. In experiment 3 is 0.1 molar, 0.10 to the X times 0.10 molar. Now I know that Y is a 1. When the exponent is a 1, I don't have to show it, but I've solved for Y now, so I don't have to keep leaving it there as just Y. Experiment 2, that's my 0.00069 molar per second equals K times 0.05 molar to the X times 0.10 molar. At this point, I can divide these two. It's going to be about 2. The K's are going to cancel. This is going to be 2 to the X. And then the 0.1 over 0.1 cancels. So once again, solve for X. X equals 1. By comparing my experiments, I found out what the value of X and the value of Y are. Okay? Now, look back at my rate law. My constants in the rate law are the ones I need to get plugged in. The value of Y is a constant. It's 1. The value of X is a constant. It's 1. There's one more constant there that we need to figure out, and that's K. K is the rate constant. Okay? I want all my constants plugged in so that then, if I'm going to set up an experiment, I can plug in whatever concentrations I want, because the concentrations are variables. I can plug in a value for the concentrations, and then from that, I can calculate the rate. So for that to work, I have to know what X, Y, and K are. All right, so how do I find K? Well, once I've found my exponents, then I can come back, plug in everything for one experiment. So experiment 1. 0.00034 molar per second equals K times 0.05 molar to the first times 0.05 molar to the first. So now I should be able to divide those over. K is going to equal 0.00034 over 0.05 squared. The units, it'll be molar on top, seconds on the bottom, that's the molar per second. And then these two come over, that'll be times molarity squared in the bottom. So let's get the number first. I got the K equals 0.136, and then molar over molar squared is going to actually become 1 over molar times seconds, which again, sometimes they might write that 0.136 molar to the minus 1, second to the minus 1. All right, now, Last thing, I think all the numbers in the problem were pretty much 2 sig figs. So I believe if you check the slides, it actually has this as 0.14 molar, or 0.14 molars to the -1, seconds to -1. Okay, that's my value of K from the first experiment. Now, we should all know that whenever you do an experiment, there's always going to be error associated with it. So if you wanted to do this properly, you would actually have to set up all 3 experiments individually, solve for K in each one of them. So you're going to get a value of K from experiment 1, get another value of K from experiment 2, get another value of K for experiment 3, and then once you get them all, you're going to average them to get the best value that you can. Okay? On the test, I would usually say just do it once, write that number down, and maybe acknowledge, just write it should be the average, but I'm in a hurry. I don't feel like doing it 3 times and averaging it. So on a test, that wouldn't be reasonable to make you do all that. But to do it the right way, you should do it that way. Okay? All right, now, the next few slides actually walk through a lot of the process that I just did. So it actually goes up to slide 20, and that's where we're going to pick up the next video.